thought today I'd talk a little bit about PDEs. I think of the topics in the pre-semester survey, this is the one that people were least interested in. So this is what I'll probably spend the least time on as a result. But I think the big takeaway of this and the homework is that for all purposes that we really care about, you should just think of PDEs as very, very high dimensional systems of coupled ODEs. Um, so let's get that in memory. Okay. Okay, so every method for solving PDEs that we care about for this course and really in life basically boils down to taking some continuous domain, splitting it up into little bins, then treating each bin as having its own ODE associated with it. And then you're going to couple those ODEs together, solve it using whatever your favorite uh, solver is for ODEs, and just don't worry about it. And this is true not just for the examples we'll do in class, but this is generally a workhorse method. For example, my group studies the Navier-Stokes equation sometimes, and we more or less do this. We use existing ODE solvers on a spectral domain. Okay, so the one thing that is, I think, useful to know about with PDEs, and this is very useful if you've got some like weird PDE that comes up in research and you're Googling what to do with it, is that you can classify PDEs based off of the order of their space and time derivatives. So the big designation that you'll find pop up is there's a hard distinction between hyperbolic and parabolic PDEs. So hyperbolic PDE is like the wave equation, has a double time derivative and a double space derivative. It's called hyperbolic because it's like t squared equals x squared, sort of it's like it would plot a parabola. Whereas a parabolic is a single time derivative and a double space derivative. And this seems like a really sort of pedantic difference, but the fundamental behavior of hyperbolic and parabolic PDEs is very different. From an information standpoint, parabolic PDEs erase information over time. They tend to smooth things out and create really kind of boring solutions. Whereas hyperbolic PDEs tend to preserve information. They give rise to solitons and other propagating objects. And so they give very different types of behaviors. And so the kinds of solvers you use for them reflect the fact that hyperbolic PDEs might have preserved topological quantities. Parabolic PDEs might have sort of globally preserved quantities and stuff like that you have to keep in track. So this sounds pedantic, but this is actually a really meaningful distinction when you're picking a solver. And today I'm going to focus on hyperbolic PDEs because I think they're cool. But the reaction diffusion systems you'll see in the homework are parabolic PDEs with a little bit of a twist. Okay, the big takeaway of this lecture is going to be that we can just solve PDEs as if they were coupled ODEs. So just to really drive that home, I'm going to use one of the integrators we implemented in 2 classes ago for all of the code today. So we implemented the fourth order Runyakuda last Wednesday. So I've literally just copy pasted that code into this notebook. I'm going to use fixed step here because I think that keeping track of step size in PDE solvers is a useful thing to have a sense of. So I'm just going to use fixed step fourth order Runyakuda. This is what it looks like. It has that awful butcher tableau, but importantly, we saw that it struck a good balance between time, cost, and accuracy. So we're just going to use this for all of our PDEs today. So I'm going to make sure that this is in my memory so I can use this ODE solver for my PDEs. Okay. So the one thing that comes up in PDEs, and I think a lot of people have seen this before, so I won't belabor this point, is, we're going to convert all of our PDEs to sets of coupled ODEs. So the way that you implement your boundary condition does matter somewhat, but that usually is just a function of how you define how you pass that coupling across your lattice. So this isn't that exciting. I'll just mention that if you haven't seen this before, the big distinction you'll see in the literature are Dirichlet boundary conditions, which specify the edge of your domain has certain fixed values of the field you're solving. So for example, if I'm solving for something like the distribution of heat across a plate using the Laplace equation, that would be like saying that, the left and right sides are at fixed pin temperatures. They have like a heat reservoir on either side. The other option that you could have would be Neumann boundary conditions. And those specify, instead of the value of the field, they specify the flux or the gradient of the field. And this would correspond to something like I have waves propagating on a rope and I have something like it's pinned to not allow a gradient at the edge because it has a fixed edge there. So Neumann boundary conditions come up quite a bit. They're a big thing in fluid dynamics where you have no slip and no flux boundary conditions. So you have a flow that's a velocity field PDE, and that can't go into the wall, so you can't have flux into the wall, but you also can't have it move tangential to the wall. So that's where you often see Neumann boundary conditions pop up. And I'm in just like everything in life, it turns out that there are intermediate cases between these two. But most of the methods, you're going to think about which one you're closest to, and then you might use a hybrid method if you have some mix of Neumann and Dirichlet. Um, yeah, and I'll mention that your boundary conditions are important for PDEs because if you use a spectral solver, these basically determine which spectrum you're going to use. We're going to use Fourier coefficients today because that's easier. But for a lot of weird things like where you have fixed boundary conditions, you have to use stuff like Chebyshev polynomials, which are maybe a little bit less intuitive than Fourier polynomials. Okay, so boundary conditions, they do matter primarily because when we use spectral methods, they'll pick the basis functions. But the only real distinction that I've seen come up regularly is just Dirichlet versus Neumann. Okay, so for all of my examples today, I'm just going to do a one-dimensional PDE. You'll do a two-dimensional one in the homework because that shows pretty pictures, so I thought it was cooler. But for now, I'll just keep it simple and do a one-dimensional system. And this is a system I like because it shows behaviors that I don't think is obvious from looking at it. Okay, so Berger's equation it describes the evolution of a compressible fluid in a really, really simplified scheme. And if you look at the structure of this equation, it has certain properties that look a little bit like the Navier-Stokes equations, maybe in certain simplifications. Importantly, it has a term that looks a lot like diffusion. So if this is something like the velocity field of a fluid, this tells me something about diffusion with maybe some viscosity there. But then it has this cross term that's nonlinear. And I say it's nonlinear because U doesn't just appear here, it also appears here. So U is effectively appears twice in one term. So if I didn't have this term here, this would just be diffusion. It would just say velocity smoothly diffuses over the domain. But we have this weird nonlinear term that sort of crosses U twice. And this looks a lot like the convective derivative in the full Navier-Stokes equations. So you can think of Berger's equation as like a simplified version of Navier-Stokes that maybe captures certain properties that we care about. Okay, and this PDE is exciting because it actually shows some really non-trivial behaviors because of the interplay between dissipation, which is a very sort of parabolic PDE type behavior, and this equation, which is going to end up looking a lot more like a hyperbolic term. Okay. So let's say I have this PDE defined on a field. So U is a function of X as well as time. The first thing I need to do in order to convert this into a series of ODEs is define my discretization scheme. And this is purely just going to be how I convert my continuous spatial field into a set of individual lattice sites that I'm going to solve using ODEs. And I think the simplest possible discretization scheme that is actually surprisingly effective for a lot of PDEs, including ones that I encounter in my own research, is just the method of lines. And the idea is that we're going to literally take the continuous spatial domain, we're going to chunk it up into discrete lattice sites, and then we're going to solve each of those as if it was a continuous time ODE. Empirists would call this a semi-discretization because we're discretizing space, but not time, technically. Okay, so I'm going to have some continuous field X, U is a function of X and T, and I want to split X up into some discrete space. In order to do that, I'm going to need to define some sort of method of coupling my different lattice sites together based off of the structure of this differential equation. So the easiest way to do this that I think a lot of folks have probably encountered before is finite differences. We've already seen these pop up before in the context of matrix methods, but PDEs are going to be where finite difference operators really are quite useful. And the idea here is that if I have some gradient type operator defined on some discretized spatial domain, I can always just approximate that operator as the difference between adjacent lattice sites on the domain, right? So if I want to take the derivative with respect to space on a finite domain, I could just take the difference between two lattice sites values of the field variable, and that's some bounded estimator of the gradient at that point. So finite differences, this is a whole field is deciding the right way to implement finite differences. But the simplest way that you could do it would be to maybe take the central difference. So you take the field 1/2 lattice site in each direction. So that's going to be convergent much faster than a one-way finite difference. And then the higher order version of that is the second order finite difference, which is just going to use the two adjacent sites as well as the current value to approximate the Laplace operator. Okay, and this isn't something that I think you'll have to use for this course, but it could come up once in a while, which is that these versions of these operators basically allow you to estimate the gradient with two calls to your lattice, right? So I just need to know the left and right sides. I need to know one more query to do the second order finite difference, and generally the number of queries increases linearly with the order of the derivative. There are cases where you might want to do a little bit better by using additional lattice sites to approximate this operator. So generally when I see finite difference operators for the Laplacian, it just uses the lattice site ahead, the lattice site behind, and the current values, so 3 values. But you could imagine using the value 2 ahead or 2 behind. So you could imagine using an entire set of values to approximate these. So there's actually a whole family of different finite difference methods. It's just that people usually just use the first order finite differences because they're easier. But you can go down this whole Wikipedia rabbit hole. So you'll notice that the coefficients here are like 1, 2, 1. But you could, if you go and you use something higher order to approximate this, you'll have a different set of coefficients, and it's given by Pascal's triangle. So I give a link to this in the notes, but if you really want to get into like deep PDE lore, there are alternatives to using this discretization. I just like this because it's simple. It's just 3 terms. Okay, so the idea here is that here, if I didn't have these terms that were that depended on space, like if a du dt was just like f of u, right, then I wouldn't need to care about space at all. I could just take each lattice site, solve an ODE. The different sites don't talk to each other. And really the idea is that these sites, these partial derivatives are what going to cause our PDEs to be coupled together. So you should almost think about gradient operators as coupling together adjacent lattice sites if I try to convert a PDE into a series of coupled ODEs. Okay, and then the coupling scheme is just defined by the definition of the finite difference operator. Okay, so in practice, all that the method of lines is going to do is it's going to say that we're going to instantiate an ODE at every lattice site, and then those ODEs are going to be coupled where like the gradient term says that this ODE has some term that depends on its current value, and then its left and right neighbors. So the idea is that this couples locally the different ODEs together. Okay, so if I take these operators and I just plug them in to Berger's equation, I get an explicit definition of my set of coupled ODEs. So I'm just going to take those operators, plug them in here. And this should be a closed definition of my series of coupled ODEs, right? So this says that each lattice site updates based off its current value as well as its 2 nearest neighbors. And if I had a lot of mesh to spare, so I had a lot of extra lattice sites, I could use a higher order approximation here, but it's not really necessary for now. Okay, so let's see how well we do. So because this is just a series of coupled ODEs, I'm going to just use my existing RK4 ODE solver. That way I don't even have to think about the actual time stepping. I can just focus on the coupling in space. Some implementation of Berger's equation is going to just focus on the discretization. Okay, so I'm going to implement each of these. I'm going to just implement this as its own class just to keep it relatively simple. So I'm going to initialize my spatial domain and my time domain. So these are going to be one-dimensional arrays that just define what my lattice points are located at. I need to give an initial condition, and then the only parameter that defines the system is the viscosity, effectively, which is this new parameter. And this will basically tell us how much this sort of like Laplacian heat equation-like behavior dominates over this sort of advection type behavior in the dynamics. Okay. And then just because it's going to be useful for these finite difference approximations, delta x is a constant. Mm-hmm.
No boundary.
I'll implement those downstream. Yeah. Okay, so delta x is a constant as long as I have a uniform mesh. So I'm just going to save delta x just because I'm going to be throwing it around here when I approximate these derivatives. But delta x should be a constant on a fixed mesh size or on a fixed mesh spacing. Okay, so in order to implement these couplings, I'm going to define sub-methods that are going to implement my gradient operators. And this is where we're going to see boundary conditions come in. So initially, just because I kind of want to be lazy, I'm going to start by just doing periodic boundary conditions. So to implement just the first order derivative, so this is just going to be this term here. I'm just going to implement my central finite difference operator. I implemented it just by taking the front half of the array and subtracting the back half of the array. There might be other ways of doing it that people prefer. You could use diff if you use diff a lot in your research. So this is going to implement the standard finite difference. So there's my dx on the bottom. And the only sort of wart about implementing it this way is what I do at the edges of the lattice. So this is where my boundary conditions are going to come in. So if I want to have something like periodic boundary conditions, that's equivalent to saying that if I have a lattice site that's at the very end of the lattice, that's coupled to the previous lattice site, and then it's going to be coupled to the one back on the front of the lattice. So periodic boundary conditions are just basically putting my PDE on a ring where it says that I need to wrap around when I compute my derivatives and use the values from the front of the array. So that ends up looking something like this, where I need to explicitly hard code what to do for my derivative at the front and back of the array. So at the front of the array, I need to use the value ahead, and then I need to use the value from the end of the array because I'm wrapping around and pulling that and then taking the derivative. So that's a little bit, weird. And then I also have to hard code what to do at the other end of the array, right? So I do the exact same thing where I use the previous value, but then I need to reach to the front of the array and use that value. So my boundary conditions purely manifest in how I define this derivative. And I'll mention that if I use a higher order approximation of the finite difference operator, so if I use something that uses multiple lattice sites, then the number of sites I need to touch when I implement my boundary conditions is going to be a lot higher because now I have a whole set of sites. It's just nice that the finite difference operator first order just needs 1 or 2 sites ahead. Okay, so that's my periodic boundary conditions just defining the first order derivative, and then I have to do the exact same sort of thing to define the Laplacian here. So the Laplacian here, I'm going to do the same thing where I'm going to pass it the array. Delta x is fixed here, so I don't have to pass that value. I'm going to implement the finite difference operator. So this is just the code version of this statement here where I take everything ahead, current value, everything behind, and divide. You'll notice that I only want to write to the middle of the array because I haven't defined how to do the edges yet. So I only use the elements 1 through n-1. I skip 0 and n-1 when I write to that. And then my boundary conditions, I once again have to hard solve for what that should be. So here I just am going to once again use current value, value ahead, value at the other end of the array, and vice versa for the other boundary condition. So this is kind of nice because I only really had to do 2 wraparounds, but you could imagine this getting out of hand if I had some really crazy spacing or something. Okay, so that's my Laplacian and my derivative. One thing you'll sometimes see me do that pops up a little bit in Python is you'll notice I've called these underscore functions. So I've started the function name with an underscore, a single underscore. Generally in Python, this is a convention. It's not a requirement. Like the compiler won't get mad at you if you don't do this. But generally in Python, there's an understanding that if a method associated with a class has an underscore, you should think of that method as effectively private. So what that means is that this derivative and Laplacian method will get called within other methods associated with the class, but you shouldn't access it from outside the class, or it's recommended not to. And unlike private methods in Java, which are strict, so if I declare a private method in Java, I cannot use it. It'll just yell at me. I can use underscore methods outside of the class. However, it's bad practice because there's an understanding that underscore methods are not supported. I'm allowed to change them at any time. And so, for example, if you're using like a lot of these machine learning packages, there will often be very nice methods that are underscore only. And if you build code that uses that method outside the class, they could change that at any time, then it'll break your code. So even though you can technically use these methods, they're just like any other method, you're really not supposed to use them outside of the class. So this is just a convention that tells people not to trust this derivative method to have a stable API. Okay, so I've defined these as underscore methods, which means I'm effectively going to use them privately only to implement logic within the class. So then the public method associated with this class is going to be the actual PDE itself. So I'm just going to write my PDE down, and it's super simple because I've already done the hard work of implementing the finite difference operator. So it's just viscosity times Laplacian minus this weird sort of advective derivative term. And these are allowed to use the underscore because this method is public, but it's using the private methods within it. And so you could imagine a universe where maybe I decide I want to completely re-implement how I do this. Maybe I want to use a different discretization or something else. And this convention tells me that as long as the right-hand side continues to work, my users shouldn't get mad at me. As long as they weren't using the underscore methods, which I'm allowed to change at will if I decide that I don't want to implement this equation this way. So there's no hard private methods in Python, but there's a convention that if it's with an underscore, you shouldn't use it outside of the method. Okay. And then just for fun, I'm going to define a call method so I can literally treat my class like a function if I want to. And this is just something I like to do whenever I have differential equations. Okay, so that's my implementation of Berger's equation. And a lot of this is sort of boilerplate code, but this at least hopefully makes clear like this distinction between things I would have as part of my own choices I've made versus things I need to have a static API. Okay, so in order to actually solve this, I need to just define what is my X lattice. I'm just going to define it on a domain that is 0 to 2 pi. I'm going to use a pretty fine mesh, so 300 lattice points. So delta x is going to be whatever 2 pi divided by 300 is. I'm going to define my t lattice. I'm going to integrate it for 50 units of time, but I'm going to have a pretty small time step, whatever 50 divided by 800 is. And then for my initial condition, I'm going to just initialize it using a sine function defined over this x domain.
So is the x and the t define your grid?
So here they're really vectors. The grid is going to be, so the grid is a one-dimensional grid in x and one-dimensional in time. But I'm not defining a full like t by x like grid. So I'm not defining like a lattice. Yeah.
Okay.
So these are just one vectors of length 300 and 800. They aren't a 300 by 800 lattice or something.
Oh
yeah. Okay. And I think I modified this to use my own code, so I'm not going to use solve by IVP. Okay, so I'm going to instantiate my model. So this will take all this lattice stuff, build the time step and all that, and also take the initial condition. And then all I'm going to do is I'm just going to touch the integrate method. And remember that the integrate method is the public method, so I'm allowed to use it. But I shouldn't use Laplacian or derivative outside of the class definition itself. Okay, so I'm just going to use a time step of, 0.01. Hopefully that's small enough. And I'm just going to integrate this equation from 0 to 50 from this initial condition. One thing you'll notice is that normally integrators take a function, but I'm allowed to treat my class as a function because of this call method. So it's just sort of a nice thing to be able to do. Okay, so when I solve that, hopefully this still works. Looks like it did. Okay, I guess something like this. So I don't think this is very readable, but I think this is. So the color here is the value of u, which is the field variable we're integrating. X is our spatial domain. T is time. People sometimes call this a chimograph. And you can sort of see what this equation does, which is that you get basically a traveling front that basically travels from left to right. So it's going from 0 to whatever, 80, I think is what I set X as. And then because I have periodic boundary conditions, when it gets over here, it wraps around and it keeps traveling. So I get this traveling shock wave that travels across the lattice. So that's one thing that you see is this traveling shock wave that sort of keeps zooming around from left to right because it's traveling on a ring. But the other thing that you can see starting to happen is that the colors are getting dimmer over time. So you can see it's very like sharp and fancy here, but then it kind of gets washed out over here. And that sort of blurring out of the features, this is the action of the Laplacian term, right? So I mentioned that like parabolic PDEs or diffusion equations basically wipe out information. And so in this equation, I have this nice shock that's forming, but then this viscosity term is trying to kill that shock. And so over time, that nice fancy behavior is getting washed out by the Laplacian term. So Berger's equation is cool because it basically captures like basically everything interesting you see in PDEs, which is it has this sort of soliton-like excitation that travels over fast timescales, but over long timescales, it has this sort of loss of information due to dissipation. And this comes fundamentally down to how big my viscosity is relative to the other term in that equation.
So very long times, like U would be like 0.
Yeah, it'll basically just go to nothing. And I tried to plot, so what I tried to plot here were evenly spaced snapshots of the domain. So the vertical thing is my field variable X, and then the different colors or different time points. It's not as nice to see as I'd like it to be, I think. I guess I could use maybe like a different set of Y values or something. I could do something like, I have an idea. Let's do like through 10 just to see the formation of the shock. Let's do. Okay, so I think I picked a little bit too close together. So let's do like through 10. So I'm just gonna show the first couple of time steps here to see what they look like. Oh, that's super nice. Great. Okay, so here I'm just looking at the first few time steps in the lattice, and I'm plotting the rainbow. It's just different time colors. And you can see that I initialize this thing as a sine wave, right? So that's my initial condition is the purple, I guess. And then you can see the first couple of time steps, that shock really quickly forms. And it looks like I might have a little bit of a numerical instability there. It just turned out that it didn't cause problems for me. So the shock actually looks basically like a triangle wave or a sawtooth wave. And then if I maybe go like, let's do like 20 to 40. Ah, nice. Now you can see that shock is kind of propagating, but its amplitude is decreasing, right? So the shock is moving from left to right over time. but it's also getting like weaker. And you'll notice that it seems like it's washing out to around 1 is the median. And then if I go like super far in the future and I do like, let's say 80 to 100, the amplitude is now like really small. So it's like a 15% variation. And then I could go like, I don't know, 100 to 100 and let's do like 130 to 150. And now it's like 10%. And basically that shock is always traveling, but its amplitude is getting smaller and smaller. So now it's like really in this very narrow dynamic range. So over really long time scales, that diffusion term is just wiping everything out. So everything cool about my PDE goes away. But over short time scales, the dynamics is dominated by that nonlinear advection term. And that's the whole idea with Berger's equation, is this tension between dissipation and this propagating front. And there's a time scale separation you'll notice, which is that there's the fast time scale of propagation and the slow time scale of wiping out that shock.
So you can increase the viscosity, right? To try to wipe it out.
Yeah, and in fact, I think I could try running that. Let me reset that to what it was before. Let's crank that up to like new equals 1. This I could get like a numerical thing. I've actually haven't tried that. Yeah, I got a numerical thing. So yeah, I could try cranking it lower to see if I can get that thing to propagate for longer. Ooh. All right. I might have gone too ambitious by using a fixed step solver here. Yeah. Yeah. I'll think about how to make that more robust. I could crank down the time step to make that thing last a lot longer, but I think I'll hold that for a future version of this. Okay. So as we just saw when I was integrating this PDE, right? Like it looks like for a given value of, so okay, so it's working in great. It looks like I picked some value of delta t implicit when I find the time lattice and another value of delta x implicit when I find the space lattice. And you can probably guess that this idea of coupling together your lattice sites might fail at some point. And this kind of makes sense because these are definitely approximations of the true derivative. And you can imagine that if delta x is really big, then this is nowhere near close to what the actual dynamics is. And this is the really killer instability that you run into in PDEs, which is when your mesh size is inappropriate compared to your time step size. This is a really critical condition for PDEs, is how you pick how fine your mesh is versus how fine your time scale is. So just to like break this thing, I'm going to try picking like an insanely large delta x. I'm going to change this to like 30. Yeah, no surprises, it kind of exploded, but in an interesting way. But this, presumably is not what the behavior of that system looks like, because there's no way to get finer scales than the initial perturbation. It still propagates, but these stripy things, there's nothing that should be causing you to get higher order like harmonics than what you see in the initial conditions. So it looks like there's some weird stability. And you can see in the cross sections that this is just like spaghetti here. Okay, so solvers fail, and the question is, can we figure out when solvers fail in order to pick delta x and delta t appropriately? Okay, so for hyperbolic PDEs, the big idea for picking time steps is something called the CFL condition. It's the Courant-Friedrichs-Lewis. Yeah, the key word there being Courant, because that's this big applied math institute. And the idea behind these is actually really simple, which is if I take a PDE that has propagating behavior, so here I'm going to do this with the wave equation, and I'll explain why in a second. I can just literally plug in finite difference approximations of all derivatives. So that's all I'm doing here is I've just plugged in finite difference for the time derivative, finite difference for the space derivative. And if you plug in chug and rearrange that, you can back out this condition that in order to avoid having a system, a numerical instability, you need to have a condition where the speed at which things travel under your wave equation, so whatever this speed is, times whatever sort of inverse speed scale is set by delta x over delta t. So those are properties of my integrator. Those usually have to be less than some constant of order 1. And the value of this constant depends on the PDE, but you should just think that for our purposes, big C is basically 1. It's a little bit different for wave equation versus different types of PDEs. And the intuition behind this is that you can derive this by solving this finite difference thing and seeing when you get an unstable growth of certain modes. That definitely works. But the basic idea is pretty simple, which is that if I have this thing that's propagating, across my PDE, I probably don't want that thing to propagate faster than one lattice site at a time, right? So if I have a giant space step or a giant time step to match, then if I have something that's propagating at this looks like this wave propagates at about like one space unit per time, this wave propagates at one space unit per time unit. You can imagine that if I have a lattice spacing that's much larger than that, or a time between snapshots that's much larger than that, effectively this wave is teleporting multiple grid sites every time I do an update. So all this condition says is that there's some speed associated with the PDE that's built into my problem. And then there's a speed associated with only traversing one lattice site per time step. And we want those two speed scales to be the same scale in order to have a stable solution to whatever this fancy finite difference solution is. And so this is nice because this ends up backing out a very strict condition for my delta x versus delta t, which is that if I have a given mesh resolution delta x, I should always make sure that my delta t is small enough to make sure that this product is of order 1. And it's even better if it's smaller than 1 because then I don't even go a full lattice site for every propagation of the solution. So as long as my PDE has a dominant speed scale associated with it, I could define a condition on delta t and delta x in order for this to be solvable. Okay, so this works for hyperbolic PDEs. That's why I use the wave equation here. And you can imagine that the wave equation has traveling waves with some fixed speeds. That's why this looks like this. For diffusion equations, you can define a similar condition called the Neumann condition. And the idea is that in diffusion equations, information doesn't travel linearly, it travels as the square root of time. And so the equivalent condition for parabolic PDEs is actually that delta t over delta x squared equals 1, multiplied by the diffusion coefficient, which is sort of like the speed scale in diffusion equations. The reason I'm going to use the CFL condition instead of the Neumann condition is it looks like what dominates my problem is the propagating part of the solution here. So I'd argue that this equation is both a little bit parabolic and a little bit wave-like, but I think that the wave-like solution is what I really want to resolve here, so I'm going to pick the CFL condition. So I'm going to guess that I'm going to have a condition like this that determines the appropriate size scale in order to get this Burger's equation solution to propagate right. Okay, so we can see this actually come up in practice. So if I look at the snapshots from the solution I did above, it looks like in the units of space, I move about 1 for every 1 unit of time that's elapsed. So if I'm using seconds, for every 1 second, this thing is moving 1 meter or something. So that means I can guess that the speed here is that c equals 1 for the units and space scale that I chose for this problem. And this would change if I changed my viscosity and other parameters, but conveniently enough, it's all 1 here. So that gives me an idea of what I need to do for my DT val. So what I'm going to do here is I'm going to re-simulate my Burger's equation, but I'm going to see what happens as I change DT. So if I have a really tiny DT, so super small time step, and I run this, it looks like it will cook a little bit. Yeah. So it looks good. So tiny time step works. That's no surprise because the wave is barely moving from time step to time step, so I don't have to worry about jumping a lattice site. Then I'm going to crank this up just a little bit. So let's try 0.02. So now I've gone up about a factor of 20 in my time step. And it looks like it still actually works. So that's good. 0.02 seems fine. But then if I go up to 0.06, so I just go up by a factor of 3 there. Yeah, then it died. So then it just like it blew up and it gave me an instability. And generally this instability corresponds to having your solution go to infinity because you have effectively a mode that grows exponentially. Okay, and then we can probably guess that 0.1 isn't going to work here, but let's just run it. Yeah. Okay, and you can actually get that time step was somewhere between 0.02 and 0.06 just by applying the CFL condition. So I know that the speed of my wave is 1, right? I saw that from looking at the solution. There's a way to get that out of your PDE usually. So if I just use the CFL condition and I rearrange this as a condition on the time step delta t, and I just set big C equal to 1, I end up backing out that the maximum time step that I could get away with is around 0.06 or a little bit greater than. So this actually gives me the time scale at which my solution dies, is that this tells me that, around 0.06 is when I'm going to start to have problems. But if I use a much smaller time scale, I'm totally good. Anything larger should die. So the CFL condition is super useful because it basically, given a lattice spacing, and the properties of your PDE tells you what you can use for your solver. And it looks like it works for Berger's equation. Okay, and a lot of fancy fluid dynamics solvers, like for Navier-Stokes, which is a hyperbolic-like equation, a lot of those implicitly use the CFL condition given your lattice spacing to decide the optimal time step. So you could do a variable step solver that also takes into account your lattice spacing using the CFL condition.
So you can change the time step, you can also change like delta X.
Yeah, I could rearrange this into a condition on delta X, because you could imagine I could have like a situation where delta T is maybe cheap or something, or like delta T is maybe something I want clamped. So then like how big of a lattice spacing can I get away with? A case where you might run into that would be a case where you're memory limited. So for example, doing these giant finite difference transforms often involves a giant matrix multiplication. So the more space steps you have, the bigger that matrix is, so you can run out of memory. So if you're memory bound, maybe you have a condition on delta X, but if you're time bound, you have a condition on delta T. Yeah. Okay. So this is one way of solving Berger's equation. I think, we've seen that seems to work reasonably well. But I'll mention that because this is kind of a nice PD that has both aspects of parabolic and hyperbolic equations, we can also use this as a test bed for using spectral methods. And the idea behind spectral methods is actually pretty cool, which is that sometimes things get a lot easier if you just change their basis. So the homework is going to really get into this because spectral methods are the natural space that reaction diffusion equations live in for various reasons. But the idea here is I'm just going to write the solution of my PDE in space in terms of some set of basis functions, which here I'm just going to use sines and cosines. So I'm going to write whatever row of x and t is in terms of like some set of Fourier coefficients. And the important thing about spectral methods is that just like normal, we assume that the amplitude of the Fourier modes is time dependent, but the modes themselves are pure space variables. So this basically implicitly separates space and time dynamics in our problem. Okay, so if you define the Fourier transform of rho like this, you can stick that in for these terms and solve it out. And you end up getting kind of a nasty expression where you have derivatives of time here. The spatial derivatives of this actually clean up nicely because it's just an exponential, so you just get like a minus k squared. And you get this kind of ugly term for the nonlinearity, and that's because nonlinear terms have the Fourier transform appearing twice. There's no simple simplification. So if I had a purely linear PDE, I would be super golden right now, right? So if I had a giant like viscosity here, so nu was really, really big, so I could ignore the nonlinear part of my PDE, then I could ignore this term. I'd have a sum over k terms. I'd have a sum over k terms. I could just solve this term by term. And that would be super trivial to solve because then I just have to solve a bunch of ODEs that just depend on k, right? So that's super nice. And then I just have to inverse transform to get back my original solution. But really the problem with spectral methods is that it's very rare that you can take it and get it in this form because often you have nonlinear terms that do not allow you to separate out all of your different coefficients and that define your Fourier transform. So spectral methods are very, very hyped up for solving PDEs, but usually if you have any sort of cross term, they're not going to get you everything you need to solve the problem. It's true that for diffusion equations, they're super simple and easy to solve, but diffusion is an easy problem to solve to begin with, so you aren't necessarily getting something for free. Okay, but this still gives an idea here, which is that I might be able to do a little bit better by doing this entire thing in the Fourier domain. So what we're going to do is we're going to resolve Berger's equation, but we're going to use this idea of spectral solutions to see if we can do any better solving it. Okay, so my solution of Berger's equation in the spectral domain is going to look almost identical to the way I did it originally, which is I'm going to have the same API for my right-hand side. So my right-hand side actually is identical to what it was before. And I'm going to put all of the spectral stuff into these private methods, which I use the underscore to denote that I'm allowed to mess with those at will because they are not protected by any sort of convention. So here I'm going to use this idea that I can write the Laplacian as just negative k squared because it's the derivative of an exponential. And then because I want to cast that back to the original domain, I actually have to do an inverse transform every time I call that. So I take the FFT of my lattice site. So now I'm in frequency space. I multiply by k squared. That's the derivative in frequency space. And then I have to inverse transform every call. And I'm going to do the same thing for the derivative. And the hope is that by doing these extra work for the Fourier transforms, I might get slightly better solutions to my problem. Okay, so nonlinear PDEs require continuous round tripping between the spectral and real bases or and ambient bases. Okay, so let's see how that implementation works. And you'll notice again, the only thing that changed was my implementation of the derivative. All right. So yeah, that looks like that worked. You'll notice it took a little bit longer, and that's because I'm computing 2 Fourier transforms for every call to the right-hand side, so that's a little bit expensive. But you'll notice that I actually didn't get this instability. So I actually got a slightly better solution here. And that's because you can basically think of the Fourier transform as being a slightly more accurate way of doing this. And if you want to get into the lore on that, there's a little bit in the book about how you can think of spectral methods as effectively preconditioning your problem. So just like we saw with large matrix multiplications, that you can do whatever you want with them, but sometimes it's better to work in a space where effectively your columns are more orthogonal. You can think of taking the Fourier transform as doing that for your field on your lattice.
So you kind of have to figure out what the appropriate time step is for a spectral method.
You should still watch your time step, but it's usually going to be a little bit more forgiving because you have slightly better convergence guarantees. And one thing I'll mention is that I didn't deal with the boundary conditions here, and that's because implicitly by using a Fourier basis, I assume periodic boundary conditions. Okay, so then the last thing I'll mention is that, okay, if I have periodic boundary conditions, I'm totally good. I can just use Fourier domain. I can just use Fourier basis functions. If you work with PDEs a lot, especially for weird geometries, it's very unlikely that you're going to want to use periodic boundary conditions. So if I have something like fixed boundary conditions, like Dirichlet or Neumann, usually you have to use more exotic basis functions that will respect those boundary conditions in a way that Fourier transforms do not. And most of the time for PDEs on fixed domains, people use Chebyshev polynomials. And so these are, Chebyshev is, I think, a little bit beyond the scope of what I want to cover in this class, but this is a set of orthogonal basis functions that's defined on the unit interval rather than an infinite domain. And you, instead of casting to a spectral basis of Fourier modes, instead your fees would be these Chebyshev coefficients.
This is for finite boundary conditions?
Yeah, like imagine I'm solving like Berger's equation on like a plate, so it just goes to the end of the plate and then it can't go anywhere or something. So there's no wraparound or something. So then I need a basis function that can respect that. Yeah, and I talk a little bit about, when you might want to use those. Okay, and then one thing I'll just leave you with, because I think it's cool, is that we just suffered through a lot of trouble to solve Berger's equation, but it actually turns out that there's an analytic solution that gives you the shock. And this is some crazy applied math lore, because there's very few hyperbolic PDEs you can do this for. So it turns out that if you substitute in this really specific expression for your field variable and you plug it through, you can actually analytically solve this for a diffusion equation in this weird proxy variable. And this is a famous idea in applied math called the Cole-Hopf transformation. If you change your basis variable, you basically can convert Berger's equation to diffusion in a nonlinear space. And this is an idea I think is powerful because it gets to this idea that like the problem looks hard, but when you rotate it to a new basis, it can look a lot simpler. Sometimes Fourier transforms can work, but sometimes some weird transformation like the Cole-Hopf transform can actually make your problem super simple. And there's rare cases where you can do this analytically, but a lot of ideas in machine learning involve taking your data, which lives in some really ugly space, and trying to find some new space where it acts a lot better behaved. All right, I'll go and wrap up there. Thank you.